Hello, welcome to Scalable CTO. I'm Bob Dickinson. Today we're going to talk about Google Spanner vector search, a little bit of an overview, how-tos, and comparing their K-nearest neighbor versus approximate nearest neighbor implementations. So first of all, Google Cloud Spanner, just very briefly, it's a scalable relational database. It's basically Google's SQL database as a service, kind of specializes in strong consistency, it's highly available, fully managed. I have a whole big podcast just before this talking about what Google Cloud Spanner is and sort of how we use it. So if you want more details about Cloud Spanner, I would check that out. We'll talk very briefly about vector or semantic search. I also have a podcast on AI where I go into a lot of detail on this. But generally speaking, vector search is a way that we use ML models to search text based on meaning. And more specifically, we use these ML text models to generate semantic vectors for chunks of text. And we store those in a database. And then we use those same models to process user input like questions to find, to get embeddings for those questions. And then we can go get the documents out of the database that most closely match those questions based on the meaning of the question, the meaning of the text in the documents. So the way it actually works is we'll get back these 768 dimensional vector embeddings for both the document text and the question text. And then we'll do a database query to collect that set of documents. And it's kind of the basis of retrieval augmented generation, or RAG, using large language models. So this is sort of how, when you ask a question to an LLM, in order to ground the answer, what we'll do is we'll take that question, we'll tokenize it, we'll get some embeddings, we'll go search a database of documents, we'll get a bunch of documents related to that question, and then we'll send those documents along with the question into the LLM. So that's kind of the primary use case for vector search. It's really just math, so you can use it for lots of things, but what people tend to be excited about using about now is the semantic search for doing RAG with LLMs. And I wanted to mention one other thing because it's sort of going to pop up if you're looking at documentation or sort of Google propaganda. Google did this really cool Vertex AI integration thing. They have a function called ML Predict, and what it allows you to do is essentially call their ML models from a Spanner query. And you can call it in a couple different ways. One of the things that you can do is you can call the Vertex AI model to generate embeddings from text in a query. So for example, if a user asks a question, you could pass that question text directly into the ML model to generate embeddings and get the output inside of the query. And the other thing you can do is you can send the results of a vector search directly to the LLM along with a prompt. And so the combination of those two things it's super clever, but it basically means you can make an all-in-one end-to-end SQL query that does an entire RAG solution. So you can basically pipe in a user question. You can have one big SQL query that essentially says, hey, go tokenize this question the user asked, go do a vector lookup, take those documents, send it into another ML model that's an LLM that's going to go answer the question with those documents and get back the result and the actual answer from the LLM. So if you are a SQL nerd who likes talking SQL all the time, you can solve your whole LLM problem, your entire end-to-end RAG solution, all in SQL in a single query. It's super cool. I don't particularly use that. I sort of like keeping those three things separate. I like being able to do my tokenization kind of in one step to be able to analyze those results and understand it and do some telemetry on it and then call my LLMs and then process the results that come back from that and sort of understand that. So I tend to like it in three pieces, but I can definitely see the argument for why you might want to do it all at once, end to end. And they claim it's higher performance and lower cost, which would not surprise me because it's all sort of happening internally. And the only reason I bring this up here is because when you're looking at the vector search stuff that I'm talking about, they sort of mix this ML Predict into everything. I mean, it's very clever and they're sort of really trying to sell people on it. So it's sort of part of every example and part of every use case. So you're going to see the ML Predict. It's not required to use that to do any of the stuff that I'm talking about with vector search, just so we're clear. So let's look at the vector search solutions in Spanner. So the first thing is you can store embeddings in SQL tables in Spanner. You can use this array of float32 type to store embeddings that you get back from their ML models. And then you can search those embeddings using two different modalities, both of which require that you have the Spanner Enterprise, which is the middle tier of Spanner, sort of. I'll give you a workaround for that in a minute. So there's K-nearest neighbor, which is a simple SQL distance function. So it's essentially a brute force application of a distance function against a bunch of embeddings in a table. And there's approximate nearest neighbor, which is this kind of SCANN indexing, which is this is a legitimate vector database solution, like that's highly optimized. And you might think, well, that's going to be better, and it might be, but I want to kind of compare the two just so you understand. And both of them support the three basic distance functions: dot product, cosine, or Euclidean. In the case of KNN, you can do that at runtime. In the case of ANN, you need to build your index and tell it which of those distance functions you're going to use, but you can use any of those distance functions. So let's look at KNN first. So KNN stands for K nearest neighbor, and the Google speak, which is the literal quote, is there that it's suitable for highly partitionable workloads. So you think, what does that mean in English? Why would they phrase it that way? What it means in English is it's brute force and it doesn't scale. So when they say highly partitionable, they mean you can break your database into a small enough set of records that you can afford to brute force calculate the distance. Another way to say that might be that you have to have a highly selective query that you're going to compute the distance based on. So essentially, it just in a query, it uses a SQL function to compute the distance between a provided embedding and the embedded stored in a column for every row that qualifies, and it sorts the results by the distance. So it's basically a table scan. Now, Spanner's fast. Like, it's fast at doing table scans, and it's fast at doing math, and it's fast at calling functions. So it might be pretty reasonable. Like, this might be a decent solution depending on a bunch of factors, which I'll talk about. But it's basically brute force. Approximate nearest neighbor, Google says, suitable for large databases, large data sets, which is true. Great. It is suitable for large data sets, but it may not be a great solution for highly partitioned data. So if you do have highly selective queries that do a lot of pre or post filtering, it may actually not be the greatest solution, even though it's a very cool piece of tech and it's highly efficient. So the way it works is it uses a specialized index to efficiently find the nearest neighbor embeddings, and it works the way kind of a real database, vector database works. So you build these purpose-built indexes that are built around your data distribution. So it's not unlike training like an ML model to build these indexes. And you pre-specify the distance algorithm to be used and a whole bunch of other parameters. It doesn't support any partitioning or pre-filtering of the embedding. So you're basically going to go against the whole, whatever that whole table is, you're going to be able to efficiently compute the things that are the closest to a target embedding, but not be able to do really any pre-filtering on that. So it's more efficient in some ways and maybe less efficient in some other ways, which I'll talk about. So Approximate Nearest Neighbor uses this technology called SCANN, which is Scalable Nearest Neighbor algorithm. It's well documented by Google Research, open source. I'll show you some links, but essentially there's a paper that explains how it works extremely well. It's also an open source repo that has the code in it that has a bunch of other statistics around it. So, and essentially, like at a very, very high level, the way you can think about it is you're going to take all of your embeddings and you're going to build a vector index, not unlike the way you train a machine learning model. So based on the distribution of your embeddings, it's going to build kind of clumps of embeddings, and it's going to identify a population centroid in the middle of that embedding that represents that set of embeddings. And when it goes through the search later, it will search those centroids, find the ones that are the closest, and then it'll use the values that are in those clumps in order to come up with a qualified smaller set of values. So it's able to do a similar sort of thing to K nearest neighbor, except highly optimized. It's going to read a very, very small percentage of the total records in the set in order to be able to do this math. The cost for that is you might lose a little bit of recall. You might not get a perfect example. There might be things that, based on the math, should have qualified in your nearest neighbor ranking, but based on this algorithm, it might have missed, and I'll talk about that in a little bit too. So let's talk about selectivity as a term in general and how it applies to databases. So selectivity refers to how much a filter reduces the number of rows in a data set. Or a filter or a set of query conditions. So something that's highly selective is going to reduce it to something on the order of 0 to 5%, and low selectivity, it might be 20 to 100%, medium sort of in between. And the choice of vector search and how you implement it is going to be heavily influenced by your normal filter selectivity. So do you usually search a relatively small portion of rows out of your data set, or do you usually sort most or all of the rows of your data set? So is your selectivity going to be high or low? And hopefully it'll be sort of clear how to apply that by the time we're done here. So I'll give you a sample. So sample vector search that has high selectivity, and this is actually relative. It's relevant to our application at TeamSpark. So let's say we have a database that has 1 million posts distributed across 1,000 groups of 1,000 posts each. So a group is an interest group. So you have groups about, knitting and race car driving and llama, husbandry and whatever. And each of those groups has posts in it. And let's say each post has a single embedding representing the post content. In reality, it's going to be chunked and you're going to have multiple embeddings. But let's just say you have one embedding per post that represents a semantic meaning of that post in an embedding. And let's say a given member is a member of 10 groups. So that means that if I'm a member of 10 groups, I have access to about 10,000 posts out of that 1 million. So about 1% of the posts in the set are posts that I am able to see. So the selectivity of that filter is 1%. And let's say I want to answer a question. So, given if I have an embedding representing a question, hey, are there any good cat pics? I want to get the 20 posts that most closely match for the given user. So out of the million posts, I want to filter to the 10,000, and then I want to sort that based on how close it matches to this question that I've asked it. So with KNN, it's pretty straightforward. It basically uses an index to efficiently filter the qualifying 10,000 posts. So it's going to go from the million to the 10,000 very quickly with an index, and then it's going to brute force the distance calculation and sort by distance. So it's going to basically compute the distance for each embedding for those 10,000 records, sort those in order, and give me back the top 20. There's a little bit of a hack we can do to make that faster, which is that if we store enough fields in the index, we can do this entirely in the index. So we can do this index only without ever having to do a table scan or read the actual records out of the table. And I'll show you how that actually works. So with KNN implementation, let's say we have this table called post. It has the post ID, the group ID, the text string, and then the embedding representing the text string. And then we create an index on the group ID, which is what we're going to filter on. And then we run this query where we say, okay, give me all the fields, including the dot product, which is a function I'm going to call, where I'm going to pass in the embedding to the query parameter, and I'm going to compare that to the embedding from each row. And the result of that I'm going to call distance. So I'm going to do that from the post table, where the group ID is group ID, order by distance, limit 20. So what it's going to actually do is it's going to go get the 10,000 records where the group ID matches the one I passed in. Then it's going to call dot product on all those things. And it's going to be able to do this all from the index. It's not going to actually have to get the record. And then it'll be able to sort them, pick the top 20, and then only when it has to do this select star to fill in all the fields is it actually going to have to do a table scan, and it's only going to have to do that for the 20 qualifying records. So all of this, except for getting the 20 actual full records, is going to be done from the index. So it'll be pretty fast. I mean, it's brute force, but it'll be fast. I also want to talk a little bit about so Google gives you these distance functions, but they charge you a significant premium to use the enterprise level in order to use these distance functions for K-nearest neighbor. And it's a little funny because if you know how these work, these are very simple functions. I had Copilot write this one for me. It took it a couple tries to get it right. These dot product and cosine and Euclidean formulas are very simple, and it's just brute force. So there's no reason to subscribe to Enterprise and pay Google extra money to be able to call this function. You can just write this function yourself or have an LLM write it for you. I didn't do that. I have the Enterprise version. I'm using that one because I'm switching back and forth between ANN and KNN. But if you just want to do KNN and it's brute force anyway, you can implement your own distance functions, and it's not hard. Just FYI. So the ANN approach is a little bit different. So what it's going to do is it's going to use the optimized vector index to quickly find the approximate best matches, right? So it can basically instantly go get me lists of thousands of records in order based on how close they are to some target, using the cool SCANN technology. But then it has to brute force match the filter criteria against the return matches until it has enough results to meet the criteria. So if you have a low selectivity query where you're basically getting all the documents back or most of the documents back, you're not even going to notice it. But if you have a really high selectivity, this could actually have some degenerate bad performance, right? Because it's going to have to get thousands of records in order to fulfill the top 20 because it's a filtering out to get the 1% that match the records for that user, right? So given that only 1% of the posts match for the user, on average, we're going to need to get the top 2,000 vector index results to get the 20 that match for the user. That's still probably going to be fast. It's going to be faster at getting 2,000. But who knows how fast, and it sort of depends, again, on the scope and the selectivity. And it could range significantly, right? Like if your particular user doesn't happen to have a lot of posts about cats, like their top 20 might be many, many thousands into the set, or maybe it might be less. So it's going to vary quite a bit. But the moral of the story is nobody's getting out of this without a table scan, right? There's some brute force. Either way you do this, there's going to be some brute force. It's a little bit different brute force, and it depends on, if you have low selectivity, then it'll be very little or maybe none. But if you have a high selectivity, there's going to be some brute force. And so that's something you need to think about when you plan this out. So let's look at the ANN implementation. The table is basically the same, except you have to give it a little bit of a hint on the embedding field to give it the dimensionality of the embedding. The index needs that. You're going to create this new kind of index called the vector index. I've sort of put in bold everything that's different about this. and you're going to pass a bunch of options to that. And so is this starting to look fun, right? You're going to pass the distance type, so that function, so it's going to be cosine distance, and then tree depth, and then number of leaves, and there's other parameters you can pass in there. So you might already be getting a little bit of a, hey, this smells complicated. And then when you go to run the query, you're going to run this approximate cosine distance function, which again is going to take some more parameters. So it's going to take the embedding passed in parameter and the embedding from the record, and then more options. So like number of leaves to search. So again, more sort of expertise required to make this work. And then we're going to force it to use that index. So we're going to do from post, and we're going to tell it has to use this index to solve this problem, which means it's going to use that index first. So that means the first thing it's going to do is it's going to apply this function to that index to generate a list of qualifying records, and then it's going to stream those through the rest of the filtering. So it's going to brute force table scan the group ID match until it gets 20 that meet the group ID. So again, this part will be super fast. And if it's low selectivity, like if you didn't have this where in there, it would be instant. The top 20 would be the top 20, you'd be done. But if this is highly selective, you might be at this for a while. So how do we choose ANN over KNN? So first of all, I'd say, do you have enough good data to build a quality vector index up front? So this is sort of like saying, do I have enough data to train a model? Because that's kind of what it is. So if you don't have a lot of data to start with, or you don't have data that you think is going to be highly representative of the data you have later, ANN might not even be an option. And frankly, if you don't have a lot of data, you probably don't need ANN. You can probably just brute force it and get away with KNN anyway. So you have to have a decent amount of data that has to be representative. Secondly, do you want to be a vector index engineer? Because those parameters are just the tip of the iceberg. Like these are complex indexes that have a lot of parameters that have to be tuned and tested. They're going to change over time. If your distribution of data changes over time, the shape of the data changes in some way, you're going to have to rebuild these things. You're going to have to sort of stay on top of this and build some expertise around it, and build some tooling around it. And the tooling that exists within Spanner doesn't exist. Like there isn't any tooling. There's no way to modify it or update an index. If you want to change any of the index parameters or update with new data, you basically have to build a new index. You have to change all your queries to point to the new index and make sure that that's the way you want it, test and deploy it, and then delete the old index. So that's not going to be fun. Are you comfortable with a single distance algorithm determined in advance? Once you're at scale and you sort of understand, that's not a big issue. But if you're just starting out, maybe you're not ready to commit yet. Are you okay with a slight loss in recall? Because ANN is going to have a slight loss in recall. KNN will be perfect recall. It'll be literally exactly the nearest neighbors in exactly the order with the exact distance calculations. ANN has some slight loss in recall. They don't quite explain exactly how to know what it is, but there's some. And then the amount of selectivity, right? If you have very high selectivity, ANN is going to provide less of a benefit. If you have low selectivity, it's going to maybe provide a lot of benefit. And so let me give you an example. Let's say you have a knowledge base with 1 million documents in it, and you've vectorized that whole thing. So you have it all stored in your database. And your use case is somebody comes into your website and they type in a question, and you go to those 1 million documents and you get the 20 that match the most closely, and you give them back. Maybe you throw it through an LLM. So if that's your use case, ANN is definitely the kind of thing you want, right? It's going to be able to hyper efficiently get those 20 documents back without any wasted effort. Maybe slight loss in recall, but probably fine. But let's say you have a different use case. Let's say you have 10 product categories, and each one of those product categories has 10 products in it. And the use case is the user comes in and they pick a product category, then they pick a product. So now you've narrowed it down to one out of 100 documents that qualify, and then they ask a question. So now the problem is, I want to go get the 20 best answers for this question out of these 1 million documents, but only 1 out of 100 of the documents is actually going to be qualifying. So now ANN with a highly selective filter isn't going to be as efficient, right? Again, it may have to get thousands of documents to satisfy that top 20 for the things that match that product in that category. So understanding the selectivity of your pre or post filtering is super important to understanding how and when ANN might have an advantage over KNN. So my recommendation would be this. I would start with KNN. You don't have to have any data. You don't have to have really any expertise. If you don't have a large data set, or if you do have a highly selective query, it's going to be fast anyway, and it'll be perfect, right? And you can take advantage of index-only filtering, and it'll be pretty fast. Like I was surprised how fast it was on some medium-sized data sets. And you can monitor your query performance. So you can use the Spanner request tag, which is a tag that you can pass in via code in your Spanner queries to make them easy to track. So it'll sort of bundle up all these KNN queries into one little bucket, and you can go back into the Spanner UX and analyze how those queries are doing, how long they're taking, how many records they're returning, that sort of thing. So you can get a little bit of telemetry, sort of understand the shape of how these things work. And you can also experiment with distance algorithms. So you can do a fair amount with KNN out of the box. I mean, you can do it right now. You can have this up in 15 minutes, right? You don't have to upgrade to enterprise if you don't want to. If you want to write your own distance function, it's just brute force. But you can do it in a way that's pretty efficient, and it'll get you going. And then I would say if you're assessing going into ANN, I would say first of all, make sure that you are actually at a point where your vector searches using KNN are starting to get slow enough that you care, because they're going to be fast to begin with until your database starts to get really big. Make sure you have a large and representative set of embeddings. If you don't have enough embeddings to actually build a good model, the benefits are going to be questionable. And make sure you have the resources and the expertise to continually invest in vector index engineering. Like somebody's going to become the owner of the vector index and have to maintain and monitor that thing. And there are a lot of knobs to turn and ongoing care and maintenance of that thing. So that would be my guidance. Start with KNN. It'll work right out of the box, super easy to do, and then move into ANN as you see the need and as you have the resources to support it. And after you deploy ANN, assuming you go that way, because KNN is just brute force, you can leave it there. You can leave it side by side. It's very easy to run them side by side. And so one of the things you can do is you can use that to verify that ANN is actually faster than KNN, or to see what the performance difference is in your actual queries with your actual selectivity. So it'd be very easy to say on every query or on some set of queries, I'm going to run the ANN and then I'm going to run the KNN and I'm going to see what the performance difference was. And you would expect for it to be worth it that the ANN would have to be significantly faster to be worth the overhead of maintaining those indexes. But find out. Like, don't guess. Don't assume ANN is going to be faster because it's magic, technology from aliens, which it is. Just test it and see. Make sure it's actually faster. And then secondly, test the recall. Because here's the thing. It's very difficult to understand from the math, like with anything to do with machine learning, how these things work. So we know the recall for ANN is not perfect, but we don't know how imperfect it is. We kind of do. You can ask. They have some formulas that you can sort of tune to determine like how much recall is acceptable and what you're willing to do about it. But even within that, to understand like what the recall misses are going to be is hard to predict. So if you always had recall problems on new data, for example, that could be pretty bad. That could be a degenerate use case that disqualified it. If you always, if your index shapes changed over time in such a way that you had recall misses that like manifested in a certain way that impacted the product, those could be pretty bad. So here's the thing you can do. Again, because KNN is sort of cheap and easy, you can run them side by side. So you can run your ANN, get your results back, and run KNN. So KNN results are going to be perfect, right? They're going to be the exact results in the exact order with the exact distance metrics. The ANN ones should have the exact distance metrics, but they might be missing, right? You're going to have some recall misses in there. So you can actually catalog exactly what the misses were. And what you should be able to do fairly easily is say like, hey, okay, when I run ANN, I'm missing at random 1 out of 10 results in the second 10 of the results, right? The first 10 are always perfect, and somewhere in the second 10, I'm missing 1 at random, and it doesn't really correlate to like freshness or anything else. You'd be like, yeah, that's great. That's fine. You know what? For the performance benefit I'm getting, that's great. But you might find that it might manifest itself in a way that you do care about. And I think what you don't want to do is, go to your leadership or your product team and to be like, hey, the recall is slightly worse. And for them to say like, well, in what way? And you're like, well, I don't know, slightly worse. It misses sometimes. To be able to say like, here's how we've observed it missing. We think this is fine. It's worth the cost benefit to, have the faster recall, to have a little bit of loss in recall. So just, that would be my advice. Verify the performance, verify the recall, make sure that you're comfortable that ANN is faster and that the recall misses are worth it. And if you have low selectivity, it probably will be. Like, it's probably going to be a no-brainer. But if you have high selectivity, it's entirely possible that KNN is going to be way simpler and just as fast, and a lot less headache for everybody, a lot less maintenance, require a lot less expertise. So I would say it's possible that if the Spanner ANN solution figures out a way to pre-filter and combine that with the SCANN, it's entirely possible that this will win all the time, that'll be the best solution all the time. But as it is now, it's just sort of a pick your poison. If you have, like in our particular use case, which is why I'm sort of harping on this, we have highly selective filtering. So for us, KNN actually works pretty good, and I think ANN, I'm skeptical that it's worth it. But again, your mileage may vary, and depending on your use case, ANN out of the box might be fine. My vote would be like, hey, let's have the Google team figure out how to combine some pre-filtering with with their SCAN technology to be able to do both at once. But until that's the case, I think there's a valid argument to be made that you really ought to compare these two things to each other and pick the one that makes the most sense for you. So hopefully that'll be somewhat instructive. It was definitely a little bit of a voyage of discovery for me to understand how these two things worked and to see them side by side and profile them. And I was a little bit surprised to find that I actually preferred KNN, which is the simpler solution of the two, at least for our immediate use case. Anyway, good luck, and I'll talk to you next time.